Hello everyone, welcome to COMP125 Principles of Computing. This is going to be the last video from Chapter 5, Computer Organization. We have already talked about the architectures of von Neumann. We have talked about four different actually subsystems, the memory, input-output, the ALU and the control unit. We have seen some examples of how the control unit actually, the machine language, the instruction set, different actually the parts of the control unit, ALU, and all of that. So in fact, this section is just talking about putting all these different subsystems that we have talked about together and see that how at the end the full computer will just work. We have talked about the memory unit. Remember, I just actually put all of those pieces together here. So we have the memory unit, that inside the memory unit you had the memory, you had the two registers MAR for the address, MDR for the data, and you also actually just had some fetch store controller that's just working as a two-sided actually light that either it just copy the content to MDR or copy from the MDR inside the memory, and the decoder that actually decode the MAR to an address, a specific address in the memory. This was the memory unit. We had talked about the ALU that was a set of circuits, different circuits for all the arithmetic operations. It also actually had a couple of actually registers, and it also has those it has some registers that keeps the operands, for example, for adding two values, for subtracting two values, and so on. So either the values, the registers will actually just send as argument as the input operands to the ALU, and the result will be actually sent back into the those registers as well. In addition to that, the three registers that we have as the comparing two values, the greater than, equal, and less than registers here, and we also actually had some input output devices and the IO controller. We had the control unit that it actually has some register to keep the program counter, the next the address of the next instruction to be executed, and some register to keep the instruction, whenever actually the instruction has been copied from the memory, it will be actually just copied into the IR. So a part of it, which is operation code, will be sent to a decoder. The decoder will actually just send out the proper signal to the corresponding unit, either to the input output, to the memory, to the ALU, to different actually parts. Okay, so this page is just show you all of those pieces that we have talked about them. So I'm going to just review all those pieces and give you a general overview how the computer will actually execute the full thing using this full unit of these four different subunits, subsystems that we have explained and talked about. So remember we said that in the von Neumann architecture, the control unit is supposed to do three phases. Execution of each program is going to be fetching the next instruction, decoding the instruction, and understand that what needs to be done, then execute it. So just activate the proper signal and send out to different units that needs to execute them. So fetch is getting the next instruction from the memory. Decode means that you decode the instruction, the operation code part of it, and see that what needs to be done. And then execute just means that you will send different signals to the corresponding units, so that we that a specific instruction will get executed. So these three steps will be actually just repeatedly executed until the program will stop. So that's why we call it one Newman cycle. We can just write it, or write it as an algorithm, just like here, that until we haven't reached to the end of the instruction, or some error hasn't actually occurred. So you will fetch an instruction. Okay, so the first phase, fetch an instruction and update the program counter. So during the fetch, we will actually just update the program counter as well. Then we will decode the instruction that has been fetched from the memory, and then we will actually send out the proper signal and execute that instruction. Then you actually just repeat, go back to the beginning if you haven't reached to the halt. So again, fetch, decode, and execute. So what type of error can happen? So it can be actually different type of errors. For example, if you are trying to access to a memory that you cannot access to it, or you are getting some instruction code, operation code that isn't valid, or you are, for example, dividing some value by 0, any type of error that actually occurred during the program and executing the program, and the computer cannot actually deal with that, the program will stop. Or if you actually naturally reach to the end of the instructions, the end of the program, which has been indicated as halt, the full execution loop will stop. So now I'm going to actually just talk about fetch, decode, and execute it one by one, because we have already actually seen different instructions that the control unit do. But I wanted to actually tell you that, okay, what is fetch? Fetch, in fact, is going to be a couple of steps. This is when you are actually just saying fetch, it means that, okay, you need to send out the address from PC, the program counter, the register program counter is containing the address of the next instruction, right? That instruction needs to be loaded from the memory, needs to be fetched from the memory. So each fetch is going to have 4 steps. First, the value of PC will be copied, will be sent to the memory unit. So it will be sent to the MAR, the memory address register. Then the signal fetch will be activated in the memory. Okay, so the content of that address inside MAR will be actually just sent to the MDR. From the MDR, you need to copy to the IR. Remember, IR was the instruction register inside the control unit. So the content of the MDR will be copied into the IR. So when it actually just sent out to the IR, now we can actually decode it. But be careful, in the fetch, we also have one more step. We always, after actually fetching the next instruction, we always update the value of PC as well. We increase the value of the program counter, because remember we mentioned that regularly in the von Neumann architecture, you execute the programs in a sequential way. Okay, so when you execute the program at the line 50, after that you are supposed to execute the program at the instruction at the address 51. Maybe the instruction that you are executing is going to it's going to be a branch instruction and jump to some other address. But that's okay, because we haven't executed the line yet. So later on, if it is supposed to be a branching instruction, the PC will be updated. But we always actually just update PC so that we are safe, even if it is not a branching. So for the next step in the loop, the PC is already updated and everything is safe. So remember, even in the control unit, we have some adder circuit just specifically actually designed for the PC. So we always actually just after each fetch, the value of PC will be updated, will be increased. So the decode phase is very simple. The decode phase, just the content of the IR, the instruction register, is going to be, the first part of it is going to be the operation code. So this part will be sent to the decoder. The rest of the, remember the rest of the instruction register is going to be some addresses and so on. So if, for example, you are doing addition, those addresses are going to be written here. Okay, this table I actually just included in the previous video as well. This is the full set of instructions that we assume that in this toy hardware that we have already designed, this is going to be the full set of instructions that we have. This is going to be just 16 instructions, and most of the examples, I mean almost all of the examples that we do in chapter 5 and chapter 6 is based on this table, so we refer to this table again and again. So I also wanted to actually just talk about a couple of these instructions here, that for example, when I'm writing load X, what would happen during the execution? Or for example, when I'm writing a store X, what would happen during the execution? So if we have something like load X, when the instruction is going to be load, a couple of things needs to be done. Load X means that the content of the address X in the memory should be uploaded, should be actually just loaded to the register R inside the ALU. Okay, so what does this mean? It means that you need to send out a signal to the memory, because you are supposed to fetch the value of X from the memory, okay, and then get back the value, copy it inside the register R. So a couple of things needs to be done. Where is the value? Where is this address X? The address X, remember the full instruction is inside the register IR, the instruction register. The first part of it was the operation code, right? And the instruction part of it, so for example, if it is just it depends on the length of the register and the length of the each instruction that you have. For example, if you are going to have in this set that we have, we can only have the full set of instruction that we have only have one argument in all of them. Okay, so the rest of it is going to be the address, okay, that we actually show it as IR address. So this is going to be an address in the memory. It will send out to the MAR inside the memory unit, okay, the memory address register. Then a fetch signal will be sent. Then the content from the MDR, the MDR is going to be the content of the memory address X, right? So that value will be actually sent to the register R inside the ALU. So when you are writing load X, in fact, all these three steps needs to be done. Or for example, when you are writing a store X, it means that you are going to copy the value from register R inside the ALU into the address X in the memory. Okay, it means that again, you have to send out this address. This is going to be that X, right? This is going to be load X. Okay, whatever is X is that address that we are going to store the content of register R. So this is going to be sent to MAR. We are going to send out a signal for a store to copy the data, right? We are going to send out the the register R into the MDR, and then we are going to send out a store signal into the memory unit. So the memory unit needs that know that it actually copied the content from the MDR into the address at MAR. I'm going to actually just look at 3 more instruction here. So for example, when we are writing add x, again, where is add x? Add x is inside the, this is the instruction, the full instruction for us, right? It's going to have the some operation code, and the last part of it is going to be that address. Okay, so this is going to be x, this is going to be add. When you are reading add x, what needs to be done? The meaning of this instruction is that whatever is the value of x will be added to the content of the register R in the ALU, and the result will remain in the register R. So what we need to do is that we need to send out this address to MAR, to the memory, right? Because we wanted to actually fetch the content of this address. So this will be actually sent to the MAR. A signal fetch will be sent to the MAR. Then whatever is the content of the MDR will be sent out to the ALU. ALU will add the to the ALU. So okay, this value will be sent to the ALU. Whatever is, for example, it will send to the ALU. So the value of MDR will be sent to the ALU. There is going to be a register R, that the value of the register R will also send to the ALU, and the output will actually go back and send to the register R as well. So sorry, I forgot to actually mention that the operation code add has been decoded, okay, and it actually sent out a signal add to the ALU. So inside the ALU, the corresponding circuit will be activated, the result will be sent out to the register R again and stored in the register R, and we are going to be done actually. So 6 steps for this instruction add. If you are executing some instruction like JUMPX, it is simple, right? Because this time it just means that whatever is the address x, this needs to be the address that the next instruction will be taken from. So you just need to copy the address x into the PC. So the where is the address x? It is in the address part of the register IR. That part will be actually copied into the PC. This instruction compare x is interesting. So remember, we in the previous examples we used the compare with 2 arguments. This compare x just basically means that you are comparing the value of x with the content, sorry, not the value of x, the value of them at the memory address x with the content of the register R. So you are comparing the content of the register, the content of the memory address x with the content of the register R. If it is greater than R, the GT register will be 1, the rest of registers will be 0. If it is equal, the EQ register will be 1, the rest of them will be 0. If it is less than, the RLT will be 1, the rest of them will be 0. Okay, so to be able to execute this, the comparison, basically it's just, I'm trying to tell you that there we don't have a specified circuit for comparison. How we execute it, we can actually execute it using subtraction, and it is actually a very nice trick. What we do here, just let's actually do it step by step. First of all, we need to take the value at the memory address x. Where is the x? X is inside R, the address part of the R. Address part of the instruction register. So that value will be sent to MAR. We fetch it. So we copy the value from MDR and send it out to the ALU. Okay, so the value of MDR will be sent out to the ALU. Also, the value of the register R will be sent to the ALU. And then what we actually just sent out as the signal of the the instruction signal that will be sent to ALU is going to be the subtraction. So inside the ALU, we calculate the content of the memory address X minus R. What does this actually tells us? If the content of the memory X minus the content of the register R is greater than 0, if it is a positive number, it means that the content of X is greater than the content of R. Okay? If it is equal to 0, it means that they are equal. If it is negative, it means that the content of X is less than the register R. So just based on the sign of the result, if it is a positive number, if it is a negative number, if it is 0, based on that, the corresponding circuit, the corresponding register EQ, GT, and LT will be activated. So we don't have a specific circuit for the comparison. Instead of that, we do it using subtraction, and then we just check the sign of the result. Either it is negative, positive, or equal to 0, and based on that we will just set the proper register. That's going to be a very nice trick. And the last example of the instructions that we have, jump GTX, it just simply means that if the it just check the value of the register GT. If it is equal to 1, it copied the address X, which is going to be at the register IR, the address part of the register IR. This part will be copied to the PC. So as simple as that. So this is going to actually just finish the section 5.3. A couple of things. I know that it might be actually just a little bit confusing at the beginning. If you see more examples and just watch the video again and again and read the textbook, do the examples, and just be careful about the address of the memory, the content of those addresses, the address of the instructions, the operation code, and this type of actually just small things, so that you don't confuse when you are writing your examples and exercises. Okay, I'm going to just talk about the last section, 5.4, very quickly. This chapter we talked about the von Neumann architecture. The thing is, when we are when actually just scientists started creating the hardware and designing better and better and better hardwares, this figure here just shows that the scale of the speed in the number of instructions that can be done per second. You can see that in the first couple of decades, the speed was actually exponential. If you think about this diagram is a logarithmic diagram. So each of these units, just the distance between them is 10. Okay, so you can see that this growth was exponential up until 1970s. From that point, the um, the actual growth rate actually became much less than the exponential growth rate. The reason is that although every year we are actually creating faster computers, if you follow the news, you will see that almost every year the different companies, produces faster and faster computer systems. But at the end, there are some limitations for the chips, and this the size of the gates and circuits that we can create. There are some physical limitations over it because of many different actually reasons. Just like, for example, we cannot actually make more number of chips on more number of circuits and gates on for example one piece of chip that we are creating, because of the heat, because of the many different actually physical restrictions that we have. So that's why scientists started to actually just thinking that maybe the issue is that the von Neumann architecture, although it was very interesting, and when we actually it started in 1946, it actually just was a big hit and helped us a lot. Maybe the time for the von Neumann architecture is over, and we need to design some computers that works in a different way. Remember, what was the characteristic of von Neumann architecture? That it executes the instructions, the programs in a sequential way. Okay, so that's why people started thinking about different actually ways to execute the programs. And it was, although actually many different models have been proposed, but most of them were just actually remain as in experimental phase or just in theoretical phase. Only the parallel processing is something that already actually have been used, and we are using it in practice. So what is parallel processing? Parallel processing means we use, instead of just having one processing unit, we are going to have a couple of processing units, and or a couple of actually, for example, arithmetic logic unit. So there have been many different models of parallel computing. Supercomputers was the very first version of the implementation of parallel processing, and nowadays you can see that even a regular laptop that you have is going to have multi-core, so it means that you have multi-processors on one computer. And also the cloud computing that you have, I'm sure that you have heard about it. There are many different actually cloud computing systems, like the Amazon, the Microsoft, Google, all of them has their own actually cloud computing systems. And maybe in the future the quantum computing would replace the von Neumann architecture. So just as a review about the parallel processing, we have SIMD, single instruction stream, multiple data streams. This part has been removed from your textbook, although it was actually available in the older version of the textbook, but it was removed in the newer version. But I thought it's going to be nice to just review that as a kind of history, because we are not using this model again anymore. What is this model? This model is going to have a single control unit, but a couple of multiple ALU unit. So each ALU is going to work on its own memory and data, but all of them are going to be controlled by one control unit. So the older supercomputers that we have was going to be designed in this model. So there was only one control unit, but there were multiple ALU, and each one is going to have access to a piece of memory. The thing about this type of actually parallel processing models is that because the control unit was centralized, all of these ALU models should be just following exactly the same architecture, and all of them at each time would exactly do the same instructions, because the control unit was centralized and it would send out one signal to all of the ALU units. And because of that, it has a lot of actually restrictions. That's why another model that is called MIMD parallel processing have been developed. In this model, we have multiple instruction streams and multiple data streams. Just basically means that we are going to have multiple units of a full computer system. Each computer is going to have its own control unit and the ALU and the memory and everything. So it's just like every local memory and processor is going to be connected to the internet. Okay, and there isn't a centralized control unit. All of the each of these units of computing, each of these computing units, they are going to have their own control unit, ALU, memory, and everything. So because of this, this model allows us to connect computers from all over the world. For example, there were a grid system that was connecting all the computers in universities in Canada. I forgot the name of this grid system, unfortunately, but it was very actually popular. And the thing about this grid was that all the computers of universities all over the Canada was connected to a grid system, so that whenever, for example, someone wanted to execute something that some big job that could not be done over a regular computer, it could actually send it out to that grid. Then that grid was actually just sent out this job to different machines which were for idle. So because all the computers over not all of them, but many computers over the different universities in Canada was connected to that system. For example, my desktop is idle. I'm not in my office. I'm not using it, so it is still connected to the internet and connected to that grid. So someone else from another university could actually connect it and use and execute something on the machine that I have, and I'm not using it. So this is the idea of the MIMD parallel processing. Although I actually just try to simplify it very much, but the cluster computing is not as easy as just connecting all these computers. The thing is, when you are writing down, we are trying to actually just execute a program over a couple of computers. You should be able to, divide your program into different pieces so that they can be executed on its own on different machines, and at the end they will get together and then you get the final result of the full program. So I'm just trying to say that this is cluster computing is going to be very complicated in terms of how you distribute the job, and then how you combine the result and get the result back. And in some actual programs, they are not able to be parallelized. So when you are writing your program, if you're going to execute it on cloud, you have to write it using some libraries that enables the parallel computing. And the last actually section, the last note, it's not actually even covered properly in your textbook, is about the quantum computing. Quantum computing is not about parallel processing. It's just, a completely different architecture than von Neumann. Quantum computing is not like the von Neumann model anymore. I have actually included some links here. It's not about actually even the binary representation, and so if you are interested, you can follow these links. One of them is from the University of Waterloo, and interestingly, the D-Wave, which is one of the biggest companies that's working on quantum computing, it is a Vancouver-based company. And even I remember a couple of years ago, UFV had a tour sent out a couple of students. You could actually register and you could go and visit the company in Vancouver. So if you are interested, I have actually just included the link to their website as well. You can have a look at their website. So now we are done with chapter 5. This week we have covered the section 5.2.4, 5.3, and 5.4. Just don't forget to do the exercises of this chapter. I have write down the pages in my textbook, so if they are different in the new edition, sorry about that.